We are discussing CBSE Standard 12, CBSE Standard 12, previous year's physics questions answers based on the topic electronic devices. Okay, so let's resume our discussion. Monochromatic light of frequency 6.0 into 10 to the power 14 Hz is produced by laser. The power emitted is 2 into 10 to the power minus 3 watt. Estimate the number of photons emitted per second on an average by the source. Okay. Next question. Draw a plot showing the variation of photoelectric current versus intensity of incident radiation on a given photosensitive surface. So first question carry 1 mark and second question carry 1 mark. This question was asked in the year 2014. Okay. So let's first check what is the estimated number of photons. Now given the frequency is given as 6.0 into 10 to the power 14 Hz, correct? Now H we know, this is the Planck's constant. This is sometimes given in the question paper itself. The Planck's constant value is 6.62 into 10 to the power minus 34 joule second. Okay, and it is given that the power emitted is 2 into 10 to the power minus 3 power. Now we know that the each photon carry 1 quantum of energy, and 1 quantum is equal to h into nu, where nu is the frequency and h is the Planck's constant. So suppose n number of photons are emitted. So total power associated with n number of photons is n into h nu, because 1 photon carry 1 quantum means 1 h nu, so n photons carry n h nu. Now this value of power n h nu is given, correct? N h nu is given. So therefore we can find out the value of n very easily, correct? Take the screenshot. Next, photoelectric current versus intensity of incident light. Okay. So there is a condition in photoelectric effect as per the quantum physics that it should meet, the incident light should meet a minimum threshold frequency. Okay. Then after which, if that frequency is met, then only photoelectrons will emitted from the surface of photosensitive metallic surface. Okay. Now if we increase the intensity of light, if the incident light meets this threshold frequency, correct, then on increasing the intensity, the photoelectric current also increases. So it's a proportional relationship. Okay, so it's a straight line passing through the origin. When no incident light incident, then the photoelectric current is 0. So straight line. Okay. Now, state briefly, next question, state briefly the processes involved in the formation of p-n junction, explaining clearly how the depletion region means this is suppose p type, this is n type. So here is the depletion region between p and n. Some of the majority charge carriers of n, which is the electrons, flows towards it. Some of the holes comes towards the n type, correct? So this is the depletion region. So briefly, the process involved in the formation of p-n junction, explain clearly the depletion region is formed. Okay. Second, using the necessary circuit diagram, show that voltage versus current characteristics of p-n junction diode are obtained in forward biasing and reverse biasing. Forward biasing means, suppose this is p type, this is n type. So when p connected with the positive terminal of the battery and n is connected with the negative terminal of the battery, it is called forward biasing. And when p is connected with the negative terminal of the battery and n is connected with the n type is connected with the positive type of terminal of the battery, it is called reverse biasing, correct? So let's understand how these characteristics are made use in the rectification, correct? Because we know that in rectification means the process of conversion of AC to DC. Okay, AC has this type of signal, DC has a smooth signal. So if you use a single diode, half of the wave gets rectified. Means it becomes only, we know that the PN junction acts and allows the direction of current flow only when forward biased. So if it is reverse biased, then it will not conduct any current in the circuit, correct? So if you use only one PN junction as a diode, then what will happen? Half of the AC will be rectified, means it is called half wave rectifier. But if you use two PN junction diode, then the entire input signal will be converted to DC, correct? Like this. Because when both the diodes are connected in the circuit in such a way that when in one signal of AC, when first diode is forward biased, second diode is reverse biased. Alternatively, in the second cycle, second diode is forward biased and first diode is reverse biased. So alternatively, one of the diode takes the responsibility to convert the AC, correct? So let's understand. Now, this is P type, this is N types. So the majority charge carriers of N types are electrons, that we know. Okay, because it is doped by pentavalent element. P type carries the positive charge carrier, that is the whole of the majority charge carriers, because it is doped with the trivalent element like aluminium. This is doped with pentavalent element like phosphorus, correct? So the majority charge carriers of P types migrate comes here, okay, because of this majority charge carriers of N types, and the majority charge carriers of N types comes in this side, correct? So this is called diffused state of charge carriers. Now this is called the depletion region. Okay, so this is the hole diffusion takes place here and the electron diffusion takes place here. So this is called the depletion region. Okay, so now you read this entire text here and take the screenshot. Now we will jump to this is the Marx distribution. So now here this is the forward bias PN junction. Okay, so PN junction in the circuit is represented like this, correct? This is the milliampere ammeter to measure the current in the circuit. This is the rheostat to change the voltage in the circuit. This is the applied source voltage, and this is the circuit when to flow this, and we can apply how much voltage is applied here using the voltmeter. Okay, so in forward bias, if you see, when the voltage is increased, the current also increases, but this in semiconductor devices, this is not as per Ohm's law. Okay, this particular law, voltage versus current, is governed by the child-Langmuir law, correct? So Ohm's law is applied only for metallic conduction. This is semiconductor conduction. Okay, here Ohm's law is not valid. And the reverse bias PN junction, what happens? This P type is becoming negative, okay, and N type become positive, correct? So in the reverse bias condition, after a particular voltage, when the breakdown happens, then this is in reverse bias condition, normally the current is 0, but if the breakdown happens because of avalanche here, then a huge current flows here. So we use this process in the Jenner diode case. Okay? So let's read this text here. So I have explained the process of graph and connection, circuit connection. Take the screenshot. Okay. Next question. differentiate between the three segments of a transistor on the basis of their size and level of doping. So how is a transistor biased to be in active state? Okay. Now, with the help of necessary circuit diagram, describe briefly how NPN transistor in common emitter configuration amplifies a small sinusoidal input voltage. Okay. So we have two types of transistors. One is NPN, another is PNP. So there are different modes of configuration: common emitter, common base, common collector. So it is in common emitter mode, correct? Now write expression for the AC current gain. So the mass carrying half of half means 1.5, half marks, 1.5 marks and half marks. This question was asked in 2014. Okay, the very good and conceptual question. So let's explain each one by one. Now first part, emitter is moderate size, doping heavily doped, base is very thin, okay, lightly doped, and collector larger in size and moderately doped. The first part is answered. Second, for transistor to be an active state, emitter base junction to be kept in forward bias. Then only the drive can happen. Base collector junction to be kept in reverse biased. Okay. The applied voltage range in the emitter base should be between 0.6 to 1 volt. This is the operating voltage required, correct? So this is condition for being in active state of transistor. Okay. Next question. So this is how this transistor is connected. Okay. So this is base, collector, emitter. Okay. Now this is the resistor in the to drive the base emitter current voltage, correct? So this is the source of AC. This is alternating source. One capacitor is connected here. This is the the voltage measurement. So this is emitter current. This is collector current. This is base current. IB means base current. IC means collector current. I is collector current. Okay. Now this is the load in the collector emitter circuit, and this is where the output is obtained. Okay, this is the output voltage signal. Okay, through a capacitor we connected it. Now small sinusoidal voltage VI is superposed on the DC base bias VBB. Okay. VBB is our DC voltage source. Okay, this is the DC voltage source. Thus, there will be sinusoidal variation in the base current. Okay, IB will change because of this superimposition. Now, this results sinusoidal variations superimposed on the collector current, IC. The amplified output is produced. This is the amplified output. If the input signal is like this, the output signal will be like this. Okay, amplified signal. As a result of this input value, small change in current IB in the base circuit controls a larger current in the collector circuit. So if you change by very small amount in this circuit, then what will happen? Output varies significantly. This is called amplification by transistor. The current gate is given by change in the collector current divided by change in the base current. So obviously, for a small change in the base current, the collector current changes significantly. Okay, so that is called the amplification. So this ratio beta is greater than 1. Correct? Now, next question. So take the screenshot of this. The given graph shows variation of photoelectric current versus applied voltage for two different photosensitive materials and for two different intensities of incident radiation. Identify the pair of curves that corresponds to different materials but same intensity of incident radiation. Okay. So let's see. So this is graph number 1, graph number 2, graph number 3, okay, and this is graph number 4. Okay, this is voltage in the x-axis and current in the y-axis. Okay, so the 4 graphs are given. So we know that different material stopping potential may be different. Stopping potential means at what voltage, at what negative voltage the current becomes 0. This is called stopping potential. Okay, therefore the graph starting from the same point on x-axis, stopping potential is unlikely to be different material, correct? So if the stopping potentials are same for this graph number 1 and graph number 2, correct? So means materials are same. Similarly for graph number 4 and graph number 3, the stopping potential is same, correct? So they are from the same material. So we know that with increase in voltage, current increased if the intensity of the incident light kept constant. Therefore, from the graph obvious, the pair 1, 3 and 2, 4 corresponds to the different materials, because see, so 2 and 4, their stopping potentials are different, okay, and variation is also different, so they are from the different material, correct? Now, this question is very conceptual question. If the materials are same, stopping potentials are also same. Now, next question. Explain with the help of circuit diagram the working of a photodiode. Write briefly how it is used to detect the optical signals. Okay. Now, this is PN junction diode. Now, photodiode. It is PN junction, transparent window is given, okay, which allows the light photons to incident on it. The photodiode is operated in the reverse bias voltage. Because why? Because P type is connected with the negative terminal, N type with the positive terminal. Such connection of devices is called reverse bias condition. Forward biasing, P type with positive, N type with negative. But this is reverse bias because P is with the negative, correct? And voltage current statistics, see, if voltage increases, then current increases, but in the first quadrant nothing is mentioned, only in the negative quadrant voltage is in the negative, so this voltage versus current graph is given and the symbol is given like this, okay. So working. So when the photon of sufficient energy enters the depletion region of semiconductor diode, it may strike an atom with sufficient energy to release electron from the atomic structure. This creates a free electron and a hole, an atom with a space for an electron. The electron is negatively charged while the holes are positively charged. The electrons and holes may remain free, or other electrons may combine with the holes to form complete atoms again. So there are one concept of hole as a charge carrier, okay, and electron as a charge carrier that we know. So in the crystal lattice. However, it is possible that the electrons and holes may remain free and be pulled away from the depletion region by the external field. Okay. In this way, the current through the diode will change and the photocurrent is produced. It is found that the current is proportional to the amount of light energy entered in the intrinsic region. The more light, greater is the number of holes and electron pairs that generated, and greater is the current flowing. So this is how it operates. Okay. Take the screenshot. When not exposed to light, the photodiode follows the normal voltage current statistics expected of a diode. In the reverse direction, virtually no current flows, but in the forward direction, it steadily increases, especially after the turn of the voltage is reached. This is modified in the presence of light. When used a photodiode, it can be seen that the greatest effect is seen in the reverse direction. Here the largest changes are observed. This property is used detecting the optical and light signal. Okay, so we have a special type of diode which operates in the reverse biasing condition called Zener diode. Okay, so next. Mention important considerations required while fabricating a PN junction diode to be used as a light emitting diode. What should be the order of band gap of a LED if it is required to emit light in the visible region? Okay. So required consideration for PN junction diode is used as a LED. First, it should emit maximum light because LEDs are for the maximum light. So it should be operated in a very high reverse voltage. Now the band gap required in LED emitting light in the visible range is 1.88 electron volt. Okay. Now output characteristic of NPN transistor in common emitter configuration is shown in the figure. So see, this is the voltage for a fixed current. Okay, how we have it. So determine dynamic output resistance, DC current gain and AC current gain at an operating point. If the common emitter voltage is 10 volt, when base current is 30 milliampere. Okay. So 3 marks question. This question is asked in the year 2013. So now we have certain parameters of a transistor. So see, when it is given, the dynamic output resistance is given by change in collector emitter voltage divided by the change in collector current. The ratio of voltage of collector emitter to the change in collector current is called the dynamic output resistance. Okay. So here it is given that 12 minus 8 volt, this is the change in collector emitter mode, okay, in this region. Okay. So then 12, it was 12 here and it is 8 here, correct? 12 here and then the 8 volt here, this is the change in the voltage. So it is 4 voltage. And what is the current increase here? 0.2 ampere is the current increase. Because of this 12 minus 8 voltage changes. Okay. So if you change this, if you check this current, okay, it is 3.6 voltage to 3.4 voltage, correct? It is in milliampere, so I have converted to ampere by multiplying 10 to the power minus 3. This is when this is fixed, 30 microampere. Okay, so at the fixed base current, when the base current is fixed at 30 microampere, then the change in collector voltage is 12 minus 8 means 4. The corresponding change in collector current is 3.6 minus 3.4, that is 0.2. So this ratio is coming around 20,000 ohm, okay, or 20 kilo ohm. So this is called dynamic output resistance. Now DC current gain, we represent current gain by beta, is collector current by base current. So corresponding collector by base current ratio we found. AC current gain is also when the collector emitter voltage is fixed. So change in collector current to the change in base current. Okay, so we have calculated this, correct? The change in collector current and change in base current, find out the ratio, then we get the beta of AC. Okay. So take the screenshot. Next question. Describe briefly with the help of circuit diagram how the flow of current carries in an PNP transistor is regulated with emitter base junction forward biased and base collector junction reverse biased. So this is 2 marks question. Let us understand PNP transistor now. Okay. This is P type is emitter, this is collector, this is base. So collector, emitter and base is always this one, but collector emitter depends moderately doped, heavily doped, lightly doped as per the doping ratio. This is decided. Now it is a single crystal containing 2 PN junction. This is one PN junction, other PN junction is this. 2 PN junctions are there. Okay. So single crystal such that there is a very thin central layer of N-type semiconductors enclosed on either side of the P-type semiconductor. So this is a very thin, depletion layer. The central layer is called the base. Okay, this central layer is called the base. This is called the base. Okay, this is how it is represented in the circuit. Correct? Now, if you see this as far as majority charge carriers in P-type, it is the holes, and here also holes, and the majority charge carriers in N-type are the electrons. Okay. So when it is forward biased means P-type with the positive terminal of the battery, and this side, the collector side, P-type is connected with the reverse biased, so it is connected with the negative terminal of the battery. Okay, this is for the base current to flow, IB. So collector current is IC, base current is IB, and the emitter current is IE. Okay, let's explain. So the emitter current is equal to the base current versus the collector current. Okay, so the emitter current is equal to the base current plus the collector current. Correct? So as shown in the above PN junction, emitter base junction is forward biased. So same thing is explained and written here. Just go through it. Take the screenshot. Next question. Define the terms cutoff voltage, threshold frequency in relation to the phenomena of photoelectric effect. Using Einstein photoelectric equation, show how the cutoff voltage and threshold frequency for a given photosensitive material can be determined with the help of suitable photograph. Okay. So we will explain both this part. First, cutoff voltage means when the collector is kept at negative potential with respect to the emitter current. Okay, so emitter current decreases rapidly as the potential becomes more and more negative. Correct? And the current becomes zero. So at a particular value of negative potential, it becomes zero. This negative potential at which the photoelectric current becomes zero is called the stopping potential, Vs, represented by stopping potential, S for stopping potential, or the cutoff voltage. Correct? Now, so stopping potential means if we apply negative voltage at a particular condition, the current becomes zero. That voltage is stopping voltage, stopping potential. Now threshold frequency is the minimum frequency for emitting electrode, that is minimum value of frequency of incident light below which no photoelectric current is emitted, no photoelectrons are emitted. Okay, and the frequency, this particular frequency is called the threshold frequency. So Einstein photoelectric equation already we have explained that the part of energy, the total energy supplied is used for what? Part of the energy is used for emitting the electron, remaining part of the energy is used to move the electrons emitted. So this is the kinetic energy, this is the work function, this is the supplied energy. So if h nu is the frequency of the incident light, then energy incident is h into nu, h is Planck's constant. If threshold frequency is nu 0, then the work function, that is the minimum energy required to emit the electron, is h nu 0, and remaining part of it is the half mv square. So this is called the Einstein photoelectric equation, correct? So later on we have simplified, taking h on the one side. So nu is equal to nu 0. Nu is the frequency of the incident radiation, nu 0 is the threshold frequency, and half mv square, this kinetic energy, is nothing but the supplied energy E into V0. Energy is E into voltage, correct? So in terms of stopping voltage, we can write like this. So this is how it is represented. Okay. Now second, experimental demonstration of this. Okay. Now this is the window to allow the incident light to incident here. Okay. So here the voltage, and this is the applied voltage between the emitter and the collector. Okay. This is the measurement, current measurement is done here. The output is obtained here. Okay. And this is the applied voltage. So the graph is like this. When the voltage is increased in the positive direction, the current increases. As the voltage reduces, the current sharply decreases and becomes 0. This particular voltage at which the current becomes 0 is called stopping voltage, correct? So now just go through this entire text. For different intensities, two graphs are plotted. For intensity I1, this is the voltage versus current graph. For intensity I2, this is the voltage versus current graph. Okay. Take the screenshot. Now stopping potential V versus Vs. Okay, this is how the graph is represented. So data point graph shown threshold frequency can be found here. Okay, so this particular, okay, this is the frequency of the incident light. So keeping intensity as, now let us see this part. Different voltage applied plotted along x-axis and the photoelectric current found plotted along y-axis. So voltage for which no current is found in the circuit is the cutoff voltage, graph shown. Now keeping the intensities of the incident light same, only the frequency is varied from the plotted. Frequency is varied. Now this particular graph is for frequency versus voltage. Okay, so this particular frequency beyond which no photoelectrons are connected is the threshold frequency. Correct. So we'll continue our discussion. Thank you very much.